The next thing I'd like to show you today is not so much something that you need to know for everyday uses, but it's something you just simply need to know. We live in a digital age, and everything that we do pretty much is based on something I'm going to show you, a little piece of mathematics I'm going to show you. Unfortunately, it's a piece of mathematics that most people have no concept of whatsoever. So I want to take just a moment to show you this, not so much for the application standpoint, but so that you'll understand that this is used around us all the time, okay? I want to talk to you about different base numerals. And what I mean by that, I've got to define the word numeral. So we call this a number typically, 189. But it's both actually. When I use the term numeral, I'm referring to the symbol that represents that amount. And we have some kind of feel for that amount because we've lived a while and we've learned how much that is. When we say number, we're actually referring to the amount, not the symbol, but the actual amount. Now, the numeral up here that I'm showing you, that is a base 10 numeral. And what I mean by that is, it is based on powers of 10. Each of the places in this numeral represent powers of 10s. 10 to the 0, which is 1, 10 to the 1, which is 10, 10 squared, which is 100. So what this actually means, if you literally break this down, it means that I have one group of 100 plus 8 groups of size 10 plus 9 singles. Okay, and that gives me the 189. You might ask, why is it 10? Well, you know, right here we go, right? All I got to do is just wiggle these things, and, you know, luckily for us, our ancestors, I guess, had 10 fingers. We have 10 fingers. And this is the number system that's evolved. If we were like The Simpsons, I don't know if you ever watched that show or not, but they have 4 fingers on each side, we'd have a different number system. All right, now here's kind of the rub. Things that we use every day, like computers, DVD players, iPods, all these things that we seem to love and are dependent upon, game stations, all these kind of crazy things, they don't understand base 10 numerals. They understand something different because they only really have 2 fingers. They have switches instead of fingers, and switches that are either on or off. So they have a completely different numeral system. Well, not completely different. It's similar to ours, but it's not based on 10. It's based on 2. It's called binary numbers, and there's only 2 digits. 0, which typically would mean the switch is off, and 1, which means the switch is on. I think I have those correct. If not, the computer science people will correct me and I'll fix it next time. So inside your computer system, here's the way here's the way it will do math. We have this string of 1s and 0s, and the place values now are not powers of 10, but they're powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. Now, for us to understand that, it has to do a little conversion and print the correct characters. But here's what this here's what this numeral represents. It means that I have one group of 28, I have one group of size 32, I have one group of size 16, I have one group of size 8, one of size 4, none of size 2, and one of just singleton. And I think if I add all this up, let me do it real quick, 160, 180, 189. So that's the same number. Okay, it's subtle here, but that's the same number. It's just a different numeral. Okay, and that's the kind of numeral that computers, Game Boys, whatever it is, that's the numeral system that they work on. Okay. Now, you may think that requires a bunch of programming. Actually, it doesn't. The cool thing about this is that even though we're talking about using a different base numeral system, all those old algorithms that we learned back in grade school still work, even though we have a different base numeral system. For example, if I wanted to add a couple of numbers, 82 and 35, okay, I think we can do this in our heads. 117? 117? I'm good with that answer. Let me convert these over to base 2. So 82 would be a group of size 64, and then a group of size 16, which I think, let's see, let me do the arithmetic here. 64, that'd be 18. Here's a group of 16, so I got 2 left. Yep, so that's correct. And then 35, well, a group of size 32, and I've got 3 left, so 2 and 1. Okay? If you add these using the old algorithms, okay, and keep in mind that when I add 1 and 1, I get 2, but 2 in base 2 would be 1, 0. So 0 and 1 is 1, 1 and 1 is 1, 0. Got to carry the 1, 1, 0, 1, 1, 1. When you convert this back, this is my group of 64, group of 32, group of 16, no 8s, a 4, no 2s, and a 1. That adds up to 117. It's the correct answer. It's all the algorithms still work. So there's nothing new algorithm-wise going on in our computers. It's just the number system the numeral system is different. One more example of that, so you just don't think it works with addition. If I multiply, okay, 16 times 5, for example, gives me 80. Well, let me do the conversion. 16 would be one group of 16, nothing left over. 5 is a 4 with a single. Remember how you multiply these? 1 times all that gives me this, and 1 times all this. I've got to move it now to right here and add, and this gives me a 64 plus a 16, which is 80. It's really slick how that all works out. Did you ever notice this one? Here's a cool one for you. Did you ever notice that numbers are divisible by 9 if you can add their digits up, and that sum is divisible by 9? Hopefully somebody's pointed that out to you. So like 189 is divisible by 9 because 1 plus 8 plus 9 is 18, and that's divisible by 9. But there's nothing really magic about the 9. It's just that it's one number less than the base 10. So if I asked a question like, well, is it divisible by 7? That's hard. We don't have a lot of divisibility things for 7. I can convert to base 8. Okay, now that requires me to do group things in this fashion: 1 singletons, and then 8s, and then 8 squared. That would convert into 2, subtract 2 64s, I'm left with 61. 7 times 8 goes into 61, and I was left with 5. And then if I add up those digits, 2 plus 7 plus 5 is 14, and that's divisible by 7, which, yeah, that number is divisible by 7. So that's a nice little way to do some divisibility things. And real quickly, I just want to show you this. There are other bases that are used pretty commonly by computer programmers. They use a base 16 system called hexadecimal. And what they have to do is replace these double-digit things in base 10 with single digits. Now, what that gets us into, and the reason they do that is because when they dump their binary stuff, it's a mess. But they can go through and clump it by groups of 4, and then get the values for each of those groups of 4 in binary, and then write it in terms of hexadecimal. So the 14 would be an E, the 11 is a B, and so forth. The cool thing is that this number and this number are the same. Okay, so that's where it applies. It's not that you'll necessarily have to do that much of it, but you need to understand that this is going on in all that digital equipment you have. All right, let's flash up some summary pages of the information I've just shown you.